Hours of endless scrolling, pages of irrelevant results. When you think you've finally found something, you're buried under a mountain of information, leading to cognitive overload. But what if there was a better way? Simply upload your research paper or enter your topic. Our advanced system quickly analyzes your content and finds the most relevant high-quality academic papers for you. No more scrolling, no more guesswork, just the papers you need, instantly. Look through the papers displayed in a modern card-style interface. View the details of the paper you like and download the ones you want to read. Want some explainability to trust this recommendation? Just visualize the graph and you can see a shortest path between your paper and the recommended paper. You can enlarge this graph, look at the attributes of a particular node, see the connections going out of each paper, and see how the two papers that were displayed were connected to each other using the shortest path. If you don't already have a paper to start with, then don't worry, you can explore the knowledge graph. For example, you're working on machine learning solutions for melanoma detection. Then you can just search for papers related to melanoma detection. Explore the search results, select a paper that you like, and click Save Details to save the details for that paper. The system will extract the metadata that you can then look at, and then get similar paper recommendations. And again, you get a list of highly relevant academic papers that you can look through, and you can also visualize the graph of the shortest path between the recommended paper and the paper that you search for. So how does it work? We combine the power of semantic and structural similarity to create a recommendation system using a knowledge graph supported by LLM Embedding. I will now explain how the knowledge graph was constructed and optimized, the algorithm developed to traverse the knowledge graph, and the use of LLM embeddings for semantic similarity. I used this dataset from Kaggle with 1 million academic papers, cleaned the dataset and stored each paper as a node, connected to cited paper nodes, authors they were written by, venues or journals that they were published in, years they were written in, and keywords their titles contained. This knowledge graph was created using Cipher query language in Neo4j. However, this led to a very sparse and inefficient representation. I then extracted domain-specific datasets, for example NLP, machine learning, robotics, after applying my article classification algorithm and reconstructed the knowledge graph. This led to a more dense and interconnected representation. I then developed a graph search algorithm that takes the metadata of a paper, for example the title, Introduction to Neural Networks, would be broken down into Introduction, Neural, and Networks using NLTK and word cleaning. After that, we generate all combinations of these keywords and then see the paper nodes that are connected to each of those combinations. This will assign an initial score depending on how many of those keywords were relating to a paper. For example, the word neural would have more than 1,000 papers connected to it. This would mean more than 4,000 initial nodes. We then expand the search from the initial nodes using BFS logic. Every node in the priority queue would have a score and a depth. At each depth level, a call will be made to Neo4j, and the neighbors of each node would be explored depending on the relationship that they're connected by. If the neighbor is visited, the score is updated. If the neighbor is not visited, then it's added to the unvisited nodes in the priority queue. Because we're using a priority queue to store the paper nodes, we're also using pruning to prioritize the paths with the highest scoring papers. The scores are calculated using an edge weighting scheme. All types of relationships, as in the edges, are assigned a score based on their importance to the relevance of a paper. For example, citation or a has keyword relationship is more important than the year or the venue that the paper was published in. So the score of a paper is the score of the previous node added to the weight of the edge that is connected to. The candidates from the previous step are now going to be passed to an embeddings model to calculate the semantic similarity. I tested different LLMs and found that the performance of OpenAI's ADA-002 model was the best in terms of MRR, which is the mean reciprocal rank, which basically assesses the quality of recommendations based on how high the most relevant item was placed. To prevent the system from having to calculate the embeddings again and again, I created a vector index for embeddings so that the embeddings for each paper could be stored in the paper node's node properties. For the final filtering, we get the stored embeddings from each of the candidate paper's paper nodes, and we also embed the query abstract. We then calculate the cosine similarity between the candidates and the query abstracts, and for the top 10 results of the cosine similarity, we print them to the user as recommendations. For the metadata extraction process, we first take a PDF file and then read it using PyPDF2. The first 3 pages are then processed using NLTK and regex, which is then sent to OpenAI using prompt engineering to get the most optimal prompt with a template so that the fields for the metadata can be extracted and sent to the backend. Final process flow then becomes user inputs a paper upload or selects using Explore Papers. The metadata is extracted, keywords are processed. We search matching papers using Neo4j and keyword combinations using the graph search process. Score propagation via BFS and weighted edges is the next step. We then select the top K candidates from the priority queue, re-rank those using embedding similarity, then find the shortest path between the 2 papers to be displayed to the user for visualization, and output the top 2 papers or the top 10 papers with the graph paths. For the backend, I've used a React Django framework so the user interacts with the React frontend. The React frontend sends data to the Django backend. Django backend makes calls to OpenAI and Neo4j. The backend has 4 classes in API view: the Upload Paper view, Explore Papers view, Analyze Paper view, and Graph Path view. Here is an example query that we tested for the paper Novel Approaches for Diagnosing Melanoma Skin Lesions Through Supervised and Deep Learning Algorithms. We can see that the results highlighted in green are highly relevant because there is some mention of computational or deep learning algorithms, melanoma detection, dermoscopy images, or skin lesions, which means that the first 8 results are highly relevant and even the last 2 are somewhat relevant. I tested many such queries and we can see the performance is really good because more than 90% of the results fall under the high relevance or the medium relevance, which means that the system is working really well, especially considering the fact that the data set is very small. Similarity is highly subjective and there are no established objective gold standards, so we conducted human experiments to see how close the performance of our system was compared to human gold standards. Here is an example that shows the effectiveness of this experiment, as we can see that 77.8% agreed on one top similar paper. The system achieved a strong hit at 1 score, correctly ranking the gold standard paper first in 6 out of 8 cases. Additionally, it achieved a perfect hit at 10, indicating that the gold standard paper was always present in the top 10. The MRR score of 82.8% further supports the conclusion that the system frequently ranks the correct paper near the top. In conclusion, I have a novel hybrid recommendation system which combines symbolic graph traversal and semantic embeddings for accurate, explainable literature recommendations. It has a modular design which supports PDF document uploads for querying, explainable graph visualizations, and embedding-based re-ranking for enhanced recommendations. We validate the performance of the system using ablation studies which confirm the superior performance of the hybrid approach over purely symbolic or semantic methods. It has a user-friendly interface which enables intuitive user interaction with a sophisticated back-end architecture. Future improvements can include fine-tuning embeddings, cloud deployment, using larger datasets, and more personalized recommendations by user logins.